In this video, we're going to take some of the principles that we covered previously when we introduced second order differential equations in a previous video, and we're going to apply them to an example involving linear motion. So first of all, if we have an object moving in a straight line, there are three parameters that we're interested in. First of all, there's the displacement of that object, or the distance that it's travelled from a given 0 point or reference point, and we give that the letter s. The velocity of the object will be its displacement with respect to time, and so we have ds by dt, the differential, the first differential of s with respect to t. And similarly, the acceleration of that object will be the second differential of s with respect to t, so that's d squared s by dt squared. So let's suppose we have an object that's moving in a straight line, and let's say that its motion is expressed by this second order differential equation here. We've got d squared s by dt squared plus k squared s is equal to 0. And so in this particular instance here, s is the linear displacement at a given time t, and k is just a constant. And let's suppose we have to find an equation solving for s, given that at time t equals 2 pi over k, the displacement s is equal to c, and the velocity ds by dt is equal to 0. These parameters will become more relevant later on, but let's return to this differential equation briefly, just to mention two things before we begin. First of all, if you've been following our previous videos where we introduced the topic of second order differential equations, we spoke about everything in terms of y with respect to x, dy by dx and d squared y by dx. Here we've got an equation in terms of s with respect to t, and that doesn't change any of our methods or our approach. The same methods that we covered in the previous video still apply here. So don't be alarmed, first of all, when we don't see any y's or x's. The approach is going to stay the same. The second thing to mention is that this particular equation doesn't have a ds by dt term. There's no first differential of s or velocity in this equation. Now, it's important to realise that this is still a second order differential equation, even though that ds by dt term isn't there. We could say that it's equal to 0 ds by dt if we wanted to include that term as well. But it's still a second order differential equation, and we're still going to use the same approaches as in our previous video. So with that in mind, the first thing that we're going to do is draw out the auxiliary equation for this particular second order differential equation. And we'll get something that looks like this: m squared plus 0m, we could say, remembering that velocity term, ds by dt, we can imagine as being 0 ds by dt. So that gives us 0m in the auxiliary equation, plus k squared, and that's still equal to 0. This turns out to be a relatively simple equation to solve because it reduces to m squared equals minus k squared. And so finding the root of this particular quadratic equation means that m is going to be equal to the square root of minus k squared, which means that m is taking the form of a complex number, since we're taking the square root of a negative term. And so that means we're going to end up with complex roots in the form of m equals plus or minus jk. In our previous video, we looked at what we can do when we're presented with roots of the auxiliary equation in the form of complex numbers, and we looked at roots in the form of m equals alpha plus or minus j beta. And where alpha is the real term and beta is the imaginary term of a complex solution. For our case here, alpha is 0 because our root m only has an imaginary term in this particular instance, plus or minus jk. So we could write out m equals 0 plus or minus jk in full form if we wanted to, and there alpha would be 0 and beta would be k. But we know that when presented with complex roots in this form, our solution must be written in the form that looks like this. S equals e to the alpha t multiplied by a cos beta t plus b sine beta t. So we're solving for the displacement S, and this particular form of our solution was one of the forms that we discussed in our previous video, depending on the form that our roots take. So remembering that in our case, alpha is equal to 0 and beta is equal to k, we can replace some terms here to find something that looks like this. S equals e to the 0t multiplied by a cos kt plus b sine kt. And since e to the power 0 is always equal to 1, this simply reduces to this. S equals a cos kt plus b sine kt. So this is our general solution. And at this point we return to the original question for the particular conditions that we were given at the start. So if you remember, we were told that when time t equals 2 pi over k, the displacement s is equal to a c, a constant, and the velocity ds by dt is equal to 0. And so what we can do here is substitute some values into our general solution, and we find we have something that looks like this. S is now c equal to a cos k 2 pi over k plus b sine k 2 pi over k. Now those k terms in the arguments of cos and sine, they cancel, and we're simply left with c equals a cos 2 pi plus b sine 2 pi. So the reason we're doing this is because our general solution that we formulated above had these two unknown constants a and b. And if we remind ourselves of some basic trigonometry, we can hopefully try to solve for at least one of these unknown constants. We have arguments of 2 pi for cos and sine, and we know that sine of 2 pi is equal to 0 and cos of 2 pi is equal to 1, providing we're working in radians. And so this simplifies down to simply c equals a, or a being equal to c. So here we've solved for one of our unknown constants, a, but to find the value of the other, b, we have to differentiate our general solution, as we saw in the previous video as well. And so here we're going to differentiate the general solution we saw before. S equals a cos kt plus b sine kt. And if we differentiate that, we find that we have ds by dt, we're differentiating with respect to t, is equal to minus k a sine kt plus kb cos kt. Again, at this point, we remind ourselves of some initial conditions. We were told that when t is equal to 2 pi over k, ds by dt, the velocity, is equal to 0. And so we can make those substitutions here. We have 0 equals minus ka sine k 2 pi over k instead of the t term now. And that's added to k b cos k, again 2 pi over k. And simplifying a little bit, the k terms cancel again in the argument of the sine and the cos terms, and we're left simply with 0 is equal to minus ka sine 2 pi plus kb cos 2 pi. And again, we remember that sine 2 pi evaluates to 0 and cos 2 pi evaluates to 1. And so this reduces down simply to kb is equal to 0. So since KB is equal to 0, either K or B must equal 0 for that to be true, and we're assuming here that the constant K is non-zero, and so B must be 0 in order to satisfy that equation. So now we know both of our constants. We said earlier that A equals C, and now we see that B equals 0. And so we can place these in the general solution we saw earlier to find the particular solution to this equation. We have S equals C cos kt plus 0 sine kt. And obviously that sine term will now disappear because it's multiplied by 0. And so we're left simply with the displacement S is equal to C cos kt. So we see that our solution to this particular second order differential equation is in the form of a simple cosine function, S equals C cos kt. And if we visualize a cosine function very quickly here, we see that S is going to take the form of something like this. It'll start at an initial value of C, down to minus C and back up to C again, and with a frequency of K. So if you remember our initial scenario, we had an object moving with linear motion. We're going to have an object that starts initially with a displacement of C. We've used just this constant C. It could have been a number or a numerical value. We've just used the letter C. But whatever C happens to be, it starts with an initial displacement of C and returns to 0 to minus C and then back to C again and repeats. We have this sort of oscillating cosine motion for this particular object, and we can only find that by solving this particular second order differential equation for S, as we've done here. So I hope you found this video useful, first of all on how we can apply the principles of second order differential equations that we covered in our previous video, but then see how we can apply them to linear motion in this particular example. In our next videos, we're going to see how we can apply these to other mechanical systems and electrical systems as well.